Okay, so in this scenario, we have a quality control process, okay? So what happens in quality control? You have like a big batch of items, right? But you can't, inspect every item in that huge batch, okay? So what happens in quality control is they go ahead and they take a random sample from that batch, okay? So we're going to randomly sample 5 items from that batch. And then if they set, beforehand, before they take that random sample, they say, okay, so if this random sample has more than, so it looks like 2 or more defective products. So if in this random sample we have 2 or more defective products, then we're going to say, you know what? That's a lot of defective products in this random sample of 5. So this whole batch is no good. And they'll throw out the entire batch. Okay? So that's the way quality control usually works. So we want to go ahead and suppose that a batch contains 5% defective products. And then we want to go ahead and solve these problems here. So first thing, make a probability distribution histogram. So on the y-axis, we'll have the probability of x, and on the x-axis, we'll have x, okay? Where x is going to be our number of defective products out of 10, or sorry, out of 5, because we're randomly sampling 5. Okay? So number of defective products out of 5. So you could have 0 that are defective. You could have 1. You could have 2. You could have 3, 4, or 5. All right. And the height of these bars are going to be the probability of x. So I need to figure out what is the probability that x equals 0. What's the probability x equals 1, etc. All right. And I'm going to use Microsoft Excel to do this. But notice that this is a binomial type situation, because I'm counting the number of defective products. And if these are randomly sampled, then we can assume that they're all independent. And there's 2 choices, either you're defective or you're not defective, right? A product is either defective or not defective. So those are your binary choices. Each sample is independent of the previous sample. And we know the probability of success being defined here as being defective. Okay. So let me go ahead and open up Microsoft Excel, and we're going to calculate those probabilities. So I'm going to make a table here in Excel. So I'm going to have x, and then I'm going to have the probability of x. Okay, so x goes 0, 1, 2, 3, 4, or 5, right? Because my sample only contains 5. The probability of x, I'm going to use binom.dist. All right, the number of successes is going to be whatever I have here. So I'm just going to click on that cell. The number of trials, so I do comma, and the number of trials is 5. The probability of success is that 0.05, right? Suppose the batch has 5% defective products, so that's 0.05. And then cumulative is false, because right now I'm figuring out the exact probability that there's exactly 0 in this sample of 5 that are defective. So exact probability, I have false there. Okay? And then press enter. And there we have it. This is the probability that x equals 0. Okay? Now, to find the probability x equals 1, 2, 3, 4, 5, I can type that in every time, right? Or I could highlight this cell, get my cursor to look like that black cross, click, and hold, and let go, okay? And Excel will automatically fill everything in for me, which is super nice, okay? So now if I were to say I were to find, double click on this one, you see I'm highlighting 2. So this is 2 successes out of 5 trials. Probability of success is 0.05, and false for an exact probability. All right. So now that I have these guys, so I need to just create my histogram. So I'm going to go 1, 2, 3, 4, 5, 6, 7. So I'm going to count by tenths placed. So 3, 4, 5, 6, 7, 8. All right, so the probability that x is 0 is 0.77. So I would go ahead and have this go all the way up, something like this. Right, I'm just doing this roughly. And then probability x is 1 is 0.23 or 0.203. So that's somewhere around right here. And then probability that x is 3 is we're getting really, or x is 2 would be the next one. So we're getting 0.02. That's really small. And then from there, we just kind of get smaller and smaller, right? So it looks vaguely like this. Okay. All right, find mu. Well, for a binomial distribution, when you recognize you have a binomial distribution, first off, mu is written like this in Greek, right? So when you have a binomial distribution, mu equals n times p. Okay. So what is n? N is your number of successes, or sorry, n is your total number of trials, right? So n, total number of trials is 5. What about p? P is your probability of success, right? So if we're counting the number of defective products, then p will be the probability of getting a defective product, right? Which we've already determined is 0.05, right? Suppose the batch has 5% defective products. So that's p. So 5 times 0.05 equals, and I can pull up Excel to do this calculation for me. So here's mu equals 5 times 0.05. Press enter, and I get 0.25. All right, what is the expected number of defective products the inspector will find? Expected number is exactly the same as mu, or the mean. Okay, the mean is the same thing as the expected number. So they're asking the same question twice, right? So my answer here is just 0.25. Okay. If they asked me to round to the nearest whole number, then I would say that I expect there to be 0 defective items in my random sample of 5, right? But if they don't, because the nearest whole number is 0, but if they don't say to round it, then just go ahead and put it as 0.0 or 0.25. Okay. What's the probability that the batch will be accepted? Accepted. So what does it mean to be accepted? Let's go back to the problem up top. If 2 or more defective products are found in a random sample of 5, then you're going to reject the batch, right? So we will reject if the probability that x, we will reject if x is 2 or more. So that's greater than or equal to 2. So you are going to accept, when will you accept the batch? You will accept the batch if x is less than 2, right? So less than 2 is the same thing as being less than or equal to 1, right? So if there's 1 defective, they won't reject the batch. They'll only reject it if there's 2 or more. So we're going to accept it if x is 1 or less. So if you're going to accept the batch if 1 is less, and we want to find that probability, we want to find the probability that x is less than or equal to 1. All right, so I can use Excel, and I can find the cumulative distribution here. Let me go to Excel. So probability that x is less than or equal to 1. All right, this is binom.dist. All right, number of trials is 1. Or sorry, the number of successes is 1 right here. The number of trials is 5. The probability of success is 0.05. And now since we want to find probability x is less than or equal to 1, we will use true for cumulative. Okay, and so there we go. That's my answer, 0.9774. Right? So 0.9774. Now, that was using the cumulative distribution function. I used true. Another way that you could have solved this question is saying, oh, you know what? Less than or equal to 1, basically that means I have 0 or 1 defects, right? Those are my two choices. So you may have decided to say, okay, so it's this number plus this number, and then press enter. And you'll get the exact same answer. Okay, so you have two different ways you could have solved this question. What's the probability that the batch will be rejected? So rejected happens when there are 2 or more defects, right? So this is, since we have this sign going in, the more than direction, right? The cumulative probability distribution function only works for less than or equal to, right? So I'll need to use the complement. Well, what's the opposite of x being more than 2 or equal to 2? More than or equal to 2. The opposite of that, right? So x, remember, can take 0, 1, 2, 3, 4, or 5. So I want 2 or more. The opposite of 2 or more is 1 or less, right? So remember, the total probability is 1. So if you take off this green piece, then you'll be left with the blue piece. All right? So we already found that probability that x is less than or equal to 1, so I'll just take 1 minus that guy, right? And I'll get my answer. If I go to Excel, the probability that x is less than or greater than or equal to 2 equals 1 minus this number here. Press enter, and we get 0.0226 if I were to round that, right? Remember, Excel will round for you. If I go home and I press these little buttons over here, okay, I can round to 4 decimals automatically using those buttons, okay? So 0.0226. Right? And just to show, I could have added up all the possible probabilities for 2 or more. So I would have taken this number here and added it to this number, added that to this number, and added that to this number, and that'll give me the same probability. Right? So doing that, it's exactly the same. Okay? So 2 or more, you can add up all the probabilities for 2 or more. All right, lastly, finding sigma. So sigma in a binomial distribution is the square root of n times p times q. So n, we know, is 5. That's my random sample of 5 items from the batch. P is 0.05. What is q? Q is 1 minus p, right? So let me go over here and write this down. So 0.05 is p. Q is 1 minus p, which will be 1 minus 0.05, which will be 0.95. Okay? 0.95. Basically, Q is, so this is the probability of success, right? P is the probability of success, so Q is the probability of failure. Okay? And remember, success and failure are defined by however you define X, right? So if we're counting the number of defects, then a success is finding a defect, right? So Q would be finding a item that's not defective. All right, so I just need to calculate this. I can use Excel for that. So let me go to Excel. That's my calculator. So sigma equals SQRT of P, so 0.0, or of N, which is 5, times P, which is 0.05, times Q, which is 0.95. Okay. Once you have that, close parentheses and press enter, and you get sigma is 0.8 or 0.78, sorry, 0.4873. Right, if I were to round that, 0.4873. 0.4873. So this is our standard deviation.